open. Okay. So, um, last time we were talking about the electrodes, and these right here being reference electrodes, right? Uh, their main duty is to keep a consistent voltage difference with whatever we're looking at, okay? And so these are going to be very consistent voltages, E's, right? That we can compare other things against, okay? They're typically going to be saturated, or they're going to have some way of having an excess so that they don't change concentration over time, okay? So this is going to be a Calomel electrode. It's going to be a very common reference electrode, one of the most common ones. Um, it is falling out of favor because you'll notice it has mercury, okay? And so it's mercury chloride in there. Its E naught is 0.268. E with a saturated KCl is this value right here. So the saturated Calomel electrode, or SCE, is what's typically abbreviated, and that's almost exclusively what you'll see it as, is SCE. If you're going to purchase these, you'll get a look at SCE probes, and then they'll have down in the bottom saturated Calomel electrode, and they'll give you the exact specs. Okay, and very, very common to find in a variety of purposes. If you go into more heavily industry field testing stuff, they will actually be packaged alongside a different electrode, a indicator electrode. Okay, so that it's a whole package with the instrument. Okay, but for lab spaces, they're separated, so you can change them out. Okay, now this is what this looks like. It's going to be a platinum wire here. You have your hole with a drainage allowed right here through a porous plug. This is going to be the mercury liquid, and then we have the mercury with the mercury chloride and the KCl in here. And finally, we have right here our plug right here, which is the porous glass wool, which will allow us to exchange our environment with the other, but it's, porous, but it keeps the stuff in there. Okay. Glass wool is used a lot. Have you ever seen glass wool and used it? No. Okay. It looks a little bit like fluffy cotton or wool. Have you ever seen insulation where they like the spray in insulation? That's very similar to glass wool, except it's like white. Okay. And so you can ball it up, and it's very commonly used as essentially a porous plug to keep things from falling out. Okay. And so this is actually the saturated KCl solution right here, and this, of course, KCl, the saturated. The nice thing is this actually really helps develop the plugs using these saturated solutions like this, or the mercury and mercury chloride right here, right? Because it actually provides a bit more structure, because they're solids. This, on the other hand, liquid, right? So this is actually going to, again, be your porous plug right here that ends right here. Then we have a little bit of glass wool to keep things from falling out and provide more structure. Okay, and that's going to allow you to exchange liquid with the outside, but not everything, right? It's going to be your salt bridge, as it were. Okay, so let's look at what this looks like in terms of indicators. What would an indicator look like versus these reference probe? So She is another very, very commonly used reference electrode. This is the standard hydrogen electrode, is what it stands for. And it's going to have a potential of negative 0.220 volts. And so this would be a She right here if we were to put it on scale, right? And what we would do then is, depending on the electrode we're using, we would then use this scale here to determine how much of an offset from what we're reading we get. Okay, so remember, these are not going to be perfectly zero. Okay, in fact, there is no actual real world electrode that would be perfectly zero all the time. Okay, that does not exist. It's better to just throw that out the window right now. Okay. And in fact, reference electrodes do actually change slightly over time, and they're not ideal, right? But for example, here we can use a Xi, and this is the assigned value of the Xi, which is the 0. This is our 0 voltage. And so whenever we do this, what we need to do is we always need to correct for that reference electrode, right? So let's say we take a silver chloride electrode like we were talking about before. We set up that previous system. And now we have this reference Xi electrode. It's measuring versus AgCl, right? So what would we measure? Well, we would not measure the 0.197 volts, would we? Because that's from 0. We're going to be measuring against this, right? Negative 0.22. Okay? And so what we'll actually get is we will get a difference of negative 0.417 if we were to actually measure this. Okay? That's how many volts we would get out of this system. If we were to measure this versus the standard calomel electrode versus a standard hydrogen electrode, this is actually what we would get. Okay? And so we would take that positive value right there, subtract it off this negative value right here, and we would get the negative 0.46 volt. Okay? And that's actually the value we would end up getting. So remember that it's always E equals the E for the indicator minus the E for the reference. Okay? And so if we're looking at these versus a SHE, this would actually just be the correction factor versus our assigned value, what we would want to correct for. You can set up your instrumentation to automatically do these corrections. Okay, and they'll automatically take minus 0.22 volts every time. Okay, and adjust all of those. This would be the actual voltage you'd end up measuring between those two, which is the math we just did here. This is just graphic. I think it's sometimes a little easier to see it graphically. Okay. So there's two major classes of indicator electrodes. There's metal electrodes. This is going to be the one we're going to talk about immediately. They're going to develop an electric potential. It's going to be in response to a redox reaction. It's going to happen at the metal surface. Typically, you're going to plate things out on them. You do have to be a little careful with these. The most common metal electrode, indicator electrode, is going to be platinum because it's very stable. It doesn't corrode that easily. It's pretty easy to regenerate. Just is a pretty ideal metal for this use case. It is not the necessarily most ideal metal. It does change over time. And if you do not actually do maintenance on these, you can get drastic drift over time. Okay? You actually have to measure these every now and then. Like, so what they do is if you're using these in an actual like environment lab, and we kind of do this already. You may have remembered, I don't know if you ever did this for a pH meter, but I think you may have in my class, at least. We take a standard that we know what the pH should be, and then we measure how much of an offset we have. Okay. And that's how you can then correct your electrodes, at least mathematically. But you would always take a standard and measure and make sure that these are still working properly and everything's working as it should. Okay. These do need to be regenerated over time. They get buildups on, which then changes the conductance. And they can get some pretty serious structural damage sometimes. So the second one is going to be ion selective electrodes. And these are going to be discussed later. They're a little bit more complicated because they actually, you have to pair up your ion. Okay, you can't just use the same electrode for everything. Right? Platinum, you just use platinum for everything. So it's going to selectively bind one type of ion. It's going to do that to a membrane. When you bind ions to a membrane, this is going to generate electric potential, very similar to how some batteries work. Okay, I don't know if you've ever seen anything that does that. It's becoming pretty common in like the electronics industry. So I see it pop up on these like press release things every now and then, which is kind of interesting. And biochemistry, it's become very common too. So that's actually become quite common in biochemistry. They use that a lot for detecting like specific proteins and specific substrates and stuff. Okay. Um, just for a side note to this, this field has heavily infiltrated biochemistry. A lot of the new biochemistry techniques are actually electrochemistry. Yeah, analytical electrochemistry. It's all they are. They're just pairing with something, some sort of antigen or binding thing or something that binds, like we had talked about last semester a little bit, but we didn't have a lot of time. So this is the reaction at the indicator electrode right here. You're going to have silver. It's going to take on an electron. When that silver ion takes on an electron, it's going to give you this solid silver. Now, where is that solid silver going to go? Where is it taking on the electron? Now, at the metal, right? And so it's going to plate onto the metal. Do note, this typically is going to make your your electrode kind of fuzzy. Okay? So instead of being this perfectly smooth, nice wire, it'll get a little rough and and that's the E naught right there. This then would be your calomel reference half cell, which is your calomel double junction saturated calomel electrode we had been talking about. This is going to have that for the E minus, right? And so when you take the difference between these, it'd be this right here, the E plus minus the E minus. For the E minus, it's a reference electrode, so the conditions, we can set them to anything we want. And in that, we just set them up so the E is the value. There you go. Okay, life is easy. Life is nice. For the other side of that, we cannot set up our own conditions, can we? We are measuring something, and so that's going to have some sort of concentration differential. Our product is silver metal. Our reactant is an ion. And so the only concentration is going to be 1 unity, right, divided by the silver metal ion. Okay. And this value goes here. This right there is that Nernst equation value that you get to use for all of these as long as you keep the temperature consistent and STP. Okay. So that simplifies that equation a bit. Solve that out. You get this right here. And so you can fairly easily just plug in a potential difference and get the concentration of silver ions. Do you understand how this worked right here? Yeah. Yeah. So when you flip that, it flips the sign, right? Yeah. Okay. Very good. Go ahead and try that out. And just try one of these for first, and then we'll go on and see. Do you want to? Do you actually want to physically try these? Or are you gonna be okay? Okay. Hopefully, Will's okay. I normally miss the whole class. Is this friends with him? Please note you can use the same shorthand calculations that we were using on like titrations and stuff to figure out the concentrations. You making good progress? Yeah. go ahead and go forward. And so what we're looking at here is we're looking at just titration, right? And so there's the fraction remaining. That's that difference between going, 100 milliliter solution of this being added, and then we get the VE is 30, right? And so we went 20 milliliter in, right? And so we've made it 66 the way there, and 33% is remaining. And so that's the fraction remaining. That's the concentration of the KCl minus from the KCl, of course. And then that's the initial volume versus the dilution factor right here, total volume, right? And so that gives us our concentration of Cl minus in the solution. So if we're trying to find the cell voltage here, we need to know the Ag plus for that solution. And how you find any system that's under equilibrium, right, is you use the KSP. Okay. And so we know the chloride one, we want this silver one on its own, and we know the KSP because we can look that up, right? And so we plug in the KSP right there. It's a 1-1 ratio, so it's just the chloride concentration down there. And that gives us our silver. We then can plug that into our Nernst equation that we had worked out in that previous little slide there. And that's the value we get right there. And so that will be our 0.1. Okay, and so the next one is very, very similar. Now we're at 40 milliliters, right? And so at that point, we're actually past our titration arm, okay? And so we have actually added an excess of 10 milliliters of AgNO3. And so that just straight up is the amount of silver in there. That's going to be the majority of the silver. Very little of it will come out from the precipitate. And so we can just plug whatever the corrected concentration, because we'll have diluted it a little bit, right? There's a dilution factor. So after our dilution factor, we plug that concentration in the Nernst equation derived that we did, and we get 0.4 voltage. Okay. If you have an already set up system, you can actually have the system after calibration, like a pH meter. Instead of giving you voltages, you can actually have it output PAG, or you can have it output the percent AG or concentrations of AG in one way or another. Okay. Typically, they do things like PAG, but you have to correct for systems in that case. So what does this look like? This is the titration curve right here. And so what we're seeing here is as the AgCl titration goes along, your Ag plus is going to increase. Your PAG is going to be equal to, of course, the negative log of the Ag plus. And so that's going to go down. It's going to decrease. And so what you'll see is your voltage here goes up. Your PAG goes down because P negative. Okay. And so again, your silver electrode is going to measure your PAG oftentimes if somebody's already set that system up. And so that would be your PAG right there. This would be how it works because you have the negative log, right? So this was already log here, right? PAG. And so we just have minus that same Nernst value, PAG. Okay? And that's all the equation would look like for the let's talk about a junction potential. So a junction potential is going to be an electric potential that exists at the interface between two different electrolyte solutions. It's going to put a fundamental limitation on the accuracy of direct potentiometric measurements. We usually do not know the contribution of the junction to the measured voltage because these are actually very complex interface systems. You can do things to simplify these junctions to some degree in some very, very, very complex experiments that are quite interesting, but I'm not going to deep dive into that. Okay. But it is an area of chemistry and physics. The development, because obsolete charged ions are going to have different diffusion coefficients, you're not going to have the exact same diffusion coefficient for a sodium, a hydrogen, a potassium, and a chloride, right? Because they're going to have different sizes, they have different charges, they're going to interact with the water slightly different. Okay? And so, for example, this is what you may think this junction looks like. This would be like the ideal case. This is, in fact, what it looks like. Okay? You have a leading edge, you have a rich region of chloride, you have a rich region of sodium, and they move at different rates into that surrounding water. Okay? And so you will get actually different voltages, different rates at that difference between the solution versus the water. Or another way of saying that, when you have an electrode in there and it's changing the concentration in one area, you have a diffusion that has to happen, right? And so this is going to build that up around that electrode, one way or the other. Okay. If you're making the charged ion, you're going to be this side. If you're making the metal part and you're removing the charged ion, you'll be that side. Okay, so these are the diffusion coefficients of these different ions in water at 25 degrees Celsius. You may have seen diffusion coefficients before. Did you see those in organic chemistry at all? Or general chemistry, excuse me. Okay. So saturated KCl is used in Saltbridge because the K plus and Cl minus have very similar diffusion coefficients. So if we look at the chloride right here, and then we look at the K plus right there, what we see is they're pretty close together, aren't they? As compared to like everything else on there, right? And so typically those are the ones you want to use together. You'll notice the other one that gets used quite a bit is like potassium nitrate. And again, they're fairly close together. Okay. Not quite as close as chloride, but pretty close. And so that's why all of the ones you see all the time, unless there's a reason you can't have chloride, are always KCl. Okay. This right here is actually your junctions for various different mixtures. And so if we have sodium chloride and KCl, this would actually be your potential right there at that junction. This is the NaCl and 3.5 molar KCl right there, and it reduces that quite a bit because this overwhelms the contribution from the NaCl. And there's some various different ones. Now, that positive sign again means that the right side of the junction becomes positive with respect to the left side. So you actually have more positive side. Again, if you have the NaCl solution placed in contact with 0.1 molar of NaO3 and sodium nitrate, which side of the junction is going to be positive? Okay, commit to an answer. What will happen is you'll have, these are millivolts. So what will happen is you're going to have your cathode and anode, and let's say that you had a 0.4 volt difference, right? So if you had this solution right here, you would have an additional negative 6.4 difference. And that would have changed the voltage you read by that 6.4 millivolt difference. So 0.00. So your reading would have been just that little bit off. Okay? And which direction it's off will depend on which direction is your sodium versus chloride. Which one has the sodium chloride on it? Which one has the KCl? Okay? Did that make more sense? Yeah. And so typically we try to avoid this issue by essentially having KCl saturated everywhere, right? Or we have a very large concentration of KCl, which has the smallest difference between these, which generates the smallest differences. And that way, if we have very large concentrations of these, we can have, very minor contributions to our voltage that we read. Okay? And that's what you're seeing. But if we mess up our system, Yeah, we can actually get fairly hefty ones for like HCl is really bad. Acids and bases in general. The H plus. Do you know why the H plus is so bad? Because it's so small. It's the smallest element, right? So an H plus is the smallest you can get, and it moves really fast. It moves like 5 times faster, 4 times faster than anything else. And so there isn't anything that's anywhere near the speed of H plus. There's no anion. The only anion that would be even close would have been H minus. That's not happening, is it? So, okay, try this real quick. Okay, so the thing you don't have to consider, sodium, right? Don't care on both sides. Just have to consider chloride versus nitrate, right? Okay, so I look at my chloride versus nitrate, right? And that's the ones that are going to be diffusing. And so the diffusion coefficient of chloride is going to be twice as great as the nitrate. And so the sodium chloride is going to deplete of chloride faster than the nitrate region will deplete of nitrate, right? And so I'm going to end up with a absence of my chloride on the sodium chloride section. And then I'm going to end up with an excess of my negative charge in comparison on the right side, well, the nitrate portion, right? Did that make sense? I didn't really specify sides. If you take this as left and this is right, then yeah. So this one right here will end up being a bit positive, right? This one will end up being a more negative than that. Mhm. And I kind of figured that you meant the first thing is left because it's on the screen. But yeah. That's why I was kind of avoiding the left right. Yeah. Okay, so what are some of the analytical consequences? Well, you're going to have a difference in your reading, right? And you're always going to have differences in your reading. Some of the worst differences are going to be for H pluses. Where do we see H plus a lot? pH meters. So pH meters actually tend to be one of the worst type of meter, and they do things to correct them and try to help the correction. That's one of the reasons why, unlike most meters that you can just calibrate like once a day or something and be okay, pH meters typically require calibrations quite often, actually, for your different conditions. Because any changes in concentrations in them is going to also create a junction potential difference. So, if we consider this junction with a pH of negative log H plus, where the H plus is the molarity of the H plus, of course, pH equals this right here. What will be the concentration of the H plus and its uncertainty? Well, the uncertainty is going to be that potential gap is going to be part of the uncertainty, right? And so if we look at this here, we're going to solve this equation first. So we're going to solve where we have pH equals the negative log of H plus for the H plus. And if the pH is the negative log of H plus, then the log of H plus equals the negative pH. And the 10 to the log of H plus is going to equal 10 to the negative pH. So if we find this uncertainty for this value right here, right, our value should be this 10 to the negative 5.214, right? But the uncertainty is going to be plus or minus 0.007 of that, right? And so all we have to do is just take the different confidence interval ranges and plug those in, don't we? And that's going to give us a result where we can use that to determine. So Again, the function for that in table 3.1, if you remember, table 3.1 was that propagating uncertainty table, is going to be 10 to the x. And so the y here is going to be our h plus here. This x here is going to be our constant, our value here, the pH value right there, plus or minus our error. And so our table tells us to figure that out, we have to take y down here, so the H plus concentration, and then our uncertainty of that y up here. And so we go ahead and plug those in, and we get, these are the values we plugged in, and that's the 0.007, by the way. And then this is actually our final value right there. So that's going to be when you solve out this right here. Mm-hmm. Remember, you're doing concentration here, so it's a pretty small number. Okay, and so there's that. So this would then finally be the relative uncertainty. So remember, we got the absolute uncertainty. We're then going to get the relative uncertainty. And that's the final answer for our actual value right here. We rounded this one up, by the way. And so it's going to be 6.1 plus or minus the 0.1, which would be the 7th here, and then times 10 to the negative 6. So that's our concentration with the uncertainty. This value over here is going to be that relative difference. So it's about 1.6 relative uncertainty percent relative uncertainty. Okay, so let's talk about some porous glass plugs, and I need to kind of pick up a little bit of speed on this. I really need to trim some of my PowerPoints, don't I? Okay, and so remember that the porous glass plugs are going to have these little glass pores in them. Whenever you're talking about glass, they're going to have oxygen ions that cause these things to bind slightly. And so what's going to end up happening is you're going to see that typically it's going to exchange the metal ions. The glass ions, on the other hand, the glass ion, oxygen ions, is going to help repel the chloride portion, the anion portion. Okay? And so that's where you're going to see these nanoporous glass plugs. They're going to have pores between 4 and 10 nanometers in diameter. This is going to reduce this flow to about 4 microliters per hour. That's not a lot of flow, right? Actually quite small. They're going to have significant errors of 10 to 100 millivolts. If the reference electrode of the nanoporous glass plug is used in a low ionic strength solution, because again, that's going to have even less exchange then. The anions do not freely pass this negative surface, but the cations can. So let's talk about micropores instead. Micropores is going to have much larger pores, okay? And so you don't get a lot of these interactions. This is going to be 100 to 3,000 nanometers. That size is just much, much larger than a typical ion, right? And so the electrolyte's going to flow, minimizing clogging and contamination of the inner electrolyte by sample components. The sample is going to be contaminated by the salt bridge flow. Can be a concern, especially if you do long-term measurements with small sample volumes. Small sample volumes meaning your concentration you're putting in is going to be larger impact, right? And long-term is going to allow these to flow longer term, right? And you'll have more concentration going through. Remember that these are significantly larger, much larger flows. You can do, of course, liquid salt bridges. It doesn't need to necessarily be a solid phase salt bridge. You can have liquids. You can have really any phase differential that you can set up will work as a salt bridge. So if you got really fancy, you could probably do something with like organic solvents and some crazy stuff. But I know that I've seen like molten salt stuff. I've seen some really crazy stuff. So the junction potential can actually be replaced with ionic liquid in place of an aqueous KCl as your salt bridge. So this KCl salt bridge is actually an ionic liquid salt bridge, and you can see actually a pretty significant drop in that. The ionic liquid will contain largely asymmetric cations and anion that do not readily crystallize, and so they won't crystallize together. They'll actually form like this weird amorphous liquid. It's usually have you ever dissolved diaper material? Ever seen that? No. I don't know how to describe it. It's have you ever put a bunch of starch in water? Seen? No. Okay. Yeah, anyways, very sort of viscous liquid sort of thing. So how ion selective electrodes work, this is going to be the second type electrode we said, hey, we'll talk about later, is this is ion selective electrodes. They abbreviate ISE because you use them a lot, actually. People design these for various different systems they want to take measurements very accurately for. So this is going to be an electrode where the potential is selectively dependent on the activity of one particular ion in solution. And so you can specifically make a silver electrode, a copper electrode, a potassium electrode, a mercury electrode, whatever. Okay, and they're not used just to measure those ions in solution. You can set up systems where that ion will change depending on something else, right? And so you'll see them used quite heavily in those as well. So these electrodes are going to be fundamentally different than the metal electrodes that we talked about before. And it's going to be in the ion selective electrodes do not involve the redox process. Okay. Have you ever heard of a concentration cell? Okay. So if you build up a concentration on one side, it's actually going to make a potential difference. Okay. Did you take biochemistry? Yes, you did. You know how there's the citric acid cycle, and then it moves hydrogens on one side of the membrane? That's a concentration cell. Your body's building up a concentration cell. It's going to make a potential energy difference, right? Which is a voltage difference between that high hydrogen H plus region and the low hydrogen H plus region. Yes. Mm-hmm. That concentration gradient will have a charge gradient. That concentration gradient will have an energy gradient as well, a voltage difference. So if you were to measure that, you would actually see a voltage difference, and that's how you would then extrapolate how much H plus there is. And that's what drives your ATP production. So again, the key feature is going to be a thin membrane here that's capable of binding only the intended ion for these ion selective electrodes. And you oftentimes can't do this absolutely perfectly, but you can do it pretty selectively. Like it gets pretty good. It's not unheard of, but it's fairly rare for there to be two ions that you can't select between. Okay. So this is actually what that looks like. Here you have your membrane. It's going to be ion selective membrane. Do you recognize this at all? Yeah, it looks a lot like a pH meter, doesn't it? Because pH meters do something very similar. So you've actually probably seen these before, but you didn't even know. Okay. And so this is your ion selective electrode. It's going to have your filling solution, your internal reference electrode right there. And then you have your membrane. The important key part is it has to be ion selective. Right here's your filling solution. It will have some pairing where you have your ion that you're looking at paired with something that stays dissolved well. Obviously, no AgCl here. Okay. Not usually, at least. So this right here is then going to be your ion selective membrane, and it's going to allow some exchange between here. And this is going to be of these cations right here, the ion you're selecting for. Okay, you can do them for negative ions as well. They're a little bit more finicky, but you can do them. And so, for example, if we use actual stuff, we could do K plus. The R minuses in here, and the ion selective electrode would then be this compound right here, which has a negative charge. And so what happens here is the K plus can come on these and then move through slowly, going to the other side. And we can bind these K pluses onto this selectively. As we bind these K pluses, that's going to change the concentration, right, of this. Now, what would the concentration here be dependent on? The solution you put in contact, right? Whatever solution you put in contact with, this concentration is going to be directly proportional to. Okay? Okay. And so the L here, this ligand portion, is going to be vanillinmycin in this case. It's your sort of structural compound that you're keeping everything attached to. Okay? You can actually use a few different things. So this is going to have an excess of negative charge as the R minuses come on. This is going to have an excess of positive charge as your C pluses come on, right? So the R minus will have an excess negative charge. The C plus will have an excess positive charge, right? So let's say that this was higher concentration. This one you're testing is lower concentration. Well, this up here is going to have a positive charge, right? And compared to this one, which will have a negative charge. Does that make sense? And so now we have a proportional voltage difference compared to whatever's in here. Okay? And all we're looking at is two concentrations. I don't know if you ever did that in general chemistry. I don't remember if I did that with you. I did a little, I think, last semester, but I don't know if we really got time to really go into it a lot because it was out at the end. Okay, so in liquid membrane ion selective electrodes, the ion selective membrane is going to be a hydrophobic organic polymer. It'll be infused with a viscous organic solution. It'll have these components, which are an ion exchanger, a ligand. This will selectively bind the analyte cation, and a hydrophobic anion. This is the hydrophobic anion we were talking about with the boron right there, the negative boron. So inside the electrode, you're going to have a filling solution. This is going to have positive and negative anions. They call it C plus B minus here. Outside the electrode, you'll have the C plus, so the same cation in this case. But it really doesn't matter exactly what your anion is. That is not the major concern. That's not what you're measuring. And you can have other ions, of course, as well. Again, it's going to select for the C plus. We had talked about potassium just a little while ago. So the voltage across the membrane is going to be measured by two reference electrode. The activity of the C plus in the analyte solution is going to change. The voltage measured is also going to change. Typically, you would recalibrate these every now and then. So this actually is your ligand here. And this is one of the key components to this, and where this is kind of start taking off. Okay, so the material science of this was not there originally. This is some new thing. This is a lot of what those like very cheap and reliable ways of measuring, silver contaminant, mercury contaminant in solution. This is actually what you're seeing. Okay. So this is going to be inside your membrane. It's going to selectively bind to the analyte ion. And one of the ways it does that is just size. Okay. So if you look at it three-dimensionally, it's going to be sized so that that ion is the only one that will associate properly with those oxygens here. Okay, so if you want to get a bigger ion, you would just increase it. Then anything that's too small is not going to associate well, and it's going to come out easily, right? Anything that's too big just can't fit. Okay, and it's just that size. You'll notice most cations have their own sizes. There's not a lot of overlap between the size. There are a few that are pretty similar in size, and those ones are the ones that are difficult to select for and can interfere with each other a bit. Okay. All right. You have any questions there? Okay. Anyways, you can do all sorts of ones of these. I'm gonna start moving forward a little bit. So the electric potential difference across a phase boundary between membrane and analyte is actually this right here. So this is the E outer here. That equals the delta G of solvation over the NF, like the equation. This then is RT over NF right here, minus this is the natural log of the activity here in the membrane versus the activity in the outer solution. Just remember that because you're looking at concentration differences, right, you should not use direct concentrations. You need to use activities because as we change concentration, the activity of solution changes, right? Yeah. So it should be activities. Note that if you do experimental measurements, like if you just straight up measure these things, these activities are the measured values. Okay? That's what you always measure experimentally. So that's why the pH meter, when we did that lab, measured activity, right? Doesn't actually measure concentration. Okay. Now, there is also a potential difference in the E inner at the boundary between the inner filling solution and the membrane, of course. You can have a boundary between them, which will it actually change your measurement. The potential difference between the outer analyte solution and the inner filling solution is actually this right here, which is E equals E outer minus E inner. Okay. This is actually our math right here. Do you need me to go through any of that? Or okay. And so this is what it would actually come out to once you do that math. And this is the formula you're probably going to be using most of the time, which is E, you'll have some constant correction factor that depends on actually quite a few factors here. One of those being the how well the cation associates this membrane. So the actual physics of that membrane would change this. Every single meter that's manufactured has a slightly different value. Okay? And so it'll have some constant. You would just measure a known solution and be able to get that constant. Okay? And then that's what you do when you test like a pH meter and you do a reference. You're doing that. Then it's going to be the same value you've always seen for Nernst equations. We had to get the in out of here because we have to have that separate because you can, again, have not a 1 plus. You can have other things, right? And then that's the activity of what you're looking at right there. Okay. This would be at 25 degrees Celsius. If you do it at different temperatures, you have to use the full Nernst equation again. It has the temperature in it, or at least separate out the temperature. Okay, so this is a glass electrode. You will notice this is directly a pH meter now. We are actually talking about the damn pH meter. I kept teasing you with, it's kind of similar, but not quite. Okay. So again, this is the glass electrode. Down here we have our glass electrode. That's that thing that people always break because they hammer down on the paper towels and break them. And this is going to be used to... This is by far and away the most common electrode people are recognize, and by far and away the most common ion selective electrode people would recognize. And the reason glass works down here is because H plus is very tiny, right? And so that actually works very nicely. Remember, glass has negative ions that are exposed. on the surface of the glass. And so the cations are the only ones coming through. Okay. And so right here we have our cap, of course. We have our leads that go to the pH meter, positive and negative leads. That's where you're getting your signal. Typically, they're put into a single socket that you screw in or plug in. This right here is the liquid level of the outer reference electrode right here, and then this is the inner reference electrode. You'll oftentimes see this. This is that blue part in our pH meters, and then this is that little tiny thing in the middle that you can see running through it. Okay, and you'll actually see in our electrodes, oftentimes this level's way lower than the inner level, which is funny because it's actually reverse of what normally should be. You can tell they're old. Still work fine though, because we do the calibrations. This right here is typically a silver wire, literally because this solution is going to be a saturated silver chloride and potassium chloride. And so that's actually what's in this inner part. So what should you store these in, by the way? Well, if you don't want the chloride, the silver chloride, this potassium chloride level to change, you would want to store them in potassium chloride. Should you ever store these dry? No. If you store them dry, this is going to evaporate, right? And then your concentrations will change drastically. You can also leach out potassium over time. And you do need to make sure that stays a consistent level. And then inside of here, the glass expands out to a bulb. And then that's right here, the porous plug. This allows a slow drainage of the electrolyte out of the electrode. This is actually where that big problem comes in, that you need to store them in potassium chloride. A lot of scientists screw that up and destroy their pH meters all the time. It's something like everybody rite passage or something. So the buffered KCl that's saturated with the silver chloride is down here in this little bulb. You'll see a liquid level. It's not always completely full because the bulb shape has little gaps right there that sometimes error develops in. And it doesn't really matter that much. It won't particularly affect anything. And so you would then, this should have AgCl suspended in here. If you run out of this, by the way, if you ever see one where you don't see like a little pellet there, it kind of looks like a streak. It is not good anymore. Get a new one. Or if you can actually, if they're expensive enough, take the cap off and refill this. It is doable. It's just a pain in the butt to do. Does you have any questions? No? Okay. The typical pH combination electrode is again going to be that silver chloride electrode. You then have H plus passing through a selective glass membrane, and then you have an outer silver and silver chloride electrode. Okay, so the connection is going to be through a porous plug. You actually have both sides of your half cells within this system. Okay. So this right here is your two half cells right here. See that? And so this is actually going to be connected right here to the analyte solution through that salt bridge. That's why that outer portion is kind of down further. So if we look at the line diagram for the represented pH electrode as it measures pH, this is going to be what it looks like. And so remember, these are different separations. So we have the outer reference electrode. We have the solid silver, phase separated from the solid AgCl, separated from the chloride. Okay, and that's your outer reference electrode. That's the electrode you're going to measure against. Okay. The electrode you're going to be having H plus interfere with is going to be the inner reference electrode. And so this one's going to be the H plus that's outside the glass electrode. That's going to be your analyte. Then our glass is going to selectively bind the H plus, allowing some of the H plus inside the glass electrode right there. this will be a proportional amount to the amount that's outside. Okay, always if you have more outside, you'll have more inside, right? It does take time to equilibrize. This is why pH meters are always, no matter how good they are, take a little while, right? And yes, you gotta wait for it to equal out. Gotcha. Okay. And so the next part is going to be the inner reference electrode right here. This is going to be the chloride right here. Phase separated from the, remember these are all aqueous right here, right? And then these are going to be phase separated from the silver chloride and the silver finally. And so you have two reference electrodes, all things being perfect. They would essentially be equal when you don't have any H plus interfering with it. And then you take on H plus and one changes, right? And that gives you a voltage difference. The amount of H plus you take on gives you more and more voltage the more H plus you take on. Okay? Because there's a larger difference between concentrations then. Now, the salt bridge is actually a porous plug at the bottom right side of the combination electrode here. This is the AgCl paste, by the way, on the the silver wire on the outer reference electrode. It kind of just is on that bottom part. Again, if you run out, you do have to replace that. So there's actually a wide variety of salt bridges you can use. That's why we typically just call them salt bridges. You can have ceramic plugs, which are very common. Platinum diaphragms, very uncommon because they're very expensive. They're very high price meters, but less likely to clog and essentially go bad on you. What usually happens is you just get ceramic plug ones, and when it stops working, you get a new one. But if you have a very, very nice one, they would hopefully have that in. This is actually the platinum diaphragm right here. Again, this would be an example of a pH meter, though typically they have plastic on the outside now instead of glass. This is what silicate glass looks like right here. And so when you see the glass right here, it's going to again have silicon with oxygens. Oxygens project out. Those oxygens have negative charge, and so cations can get in there and associate, and that allows exchange of the cations. Especially H plus, being the fastest diffuser, is going to be by far and away the most heavily exchanged and the one that can actually get through this silica glass in any sort of speed. Okay. This is actually what that looks like if you zoom in a bunch. This is crystalline. This is amorphous. Can you see the difference between those, by the way? Yeah, it's kind of stark, isn't it? So yeah, this looks like nicely organized like a tile floor. And this one just is like somebody threw paint. Yeah. Okay. So this is actually the cross section of this and what it looks like. So what you would see here is you have an internal solution. You have a dry glass layer. All sites are going to be occupied by sodium in that case. And then you have an exchange site on the other side, which is going to be your external solution here. So you have internal, external. The activity of the H plus is actually fixed in the internal. The activity is variable on the external. And so what's going to end up happening is you're going to exchange the H plus and the sodiums on the external. This is going to cause this voltage difference between here to change. And it's going to allow the H plus to exchange differently with the sodiums on this. So the metal ions in these hydrated gel regions of your membrane are going to diffuse into the glass. These are the hydrated gels, by the way, right here on the surface of the glass. And so H plus can diffuse into the membrane to replace our metal ions. This will reaction as the H plus replaces is going to be the ion exchange equilibrium. The pH electrode is going to respond selectively to H plus because the H plus is the ion that binds selectively to the hydrate gel. This is actually the old Arnold Beckman, one that was invented at Caltech. It was the first sort of portable testing, and this is a pH meter from 1935. So they've been around for a while, and of course, this revolutionized chemical testing, especially out in the field. There's never been a methodology you could do out in the field except for like chemical reactions to test. So the potential difference is going to be measured by the inner and outer silver chloride reference electrodes. Remember, we have two of them. And so it's going to depend on the chloride concentration in each electrode compartment and the potential difference across the glass membrane. So the chloride is going to be fixed in each compartment. The H plus is fixed on the inside of the glass membrane. The outside, however, has variables. So that's the only variable factor that's going to change depending on your pHs. The complexity of this is why we always have to calibrate these. We actually just, like, it seems complex mathematically, but remember that we can sum up all this stuff as constant, and then we can just test, right, to get the constant. We don't have to calculate the constant for every single electrode. That's why you always have to calibrate, because they're going to change, actually. So it's just not worth it. So the beta is going to be the electromotive efficiency. And so the response of your glass electrode is going to be equal to the constant plus beta times that Nernst equation value. This can be the log of the activity of H plus outside. And so you always end up measuring the activity at the H plus outside, right? Now, note that if your activity is negligible, that activity coefficient is negligible, or you just don't care, you'd be measuring the pH, right? Because the activity is going to be proportional to the pH. It's the activity coefficient times the pH. Okay? And so this is, again, the negative log of this value is the pH, right? That's what you're actually measuring. Okay, so what do you do when you calibrate a pH electrode? So the glass pH electrode has to be calibrated. You have to use a minimum of 2 standard buffers. Better electric systems use 3 typically, so you have some degree of error. It has to be calibrated at the same temperature as the unknown, because temperature would actually change the equation. Okay? So typically you do this at room temperature, but if you were going to do this at higher temperature, lower temperature, what would you do to your buffers? Let's say you're going to do this in ice bath. You want the pHs in the ice bath later. Well, how do you measure your buffers? Same. All right, ice bath. Keep it consistent. So the calibration needs to be repeated every 2 hours. In labs, experiment labs, that usually is not an issue, but that's why it was like, remember when we were doing the pH meters? We have 3-hour labs. I was like, if you take too long, we're going to have to recalibrate this. Okay? Okay. And so this right here is the actual equation of this. What you'll notice here is it's just a linear equation. That's all we're doing here. Because it's going to be a linear response here. Okay? So we take these 2 pHs. This would give us a calibration line, which we're figuring out the slope so that we can use a calibration line, right? And then this was then going to correct any E value that we measure. That's going to then give us the pH value if we fit it to that calibration line, right? That's all you're doing. And so this right here would actually be the pH values of various National Institute standards and technology buffers. And that's what you get on those packs. You get the little pack, and it says it is 4.007 plus or minus whatever, right? And so that's potassium, hydrogen, phthalate. Okay? And that's what you're seeing right there. So let's talk about the storage and cleaning. Store an aqueous solution to prevent dehydration of the glass. It should be a very similar activity to what's inside. Ideally, it would actually be a matched activity with KCl. Okay? But if you can't get that, some aqueous solution with concentration that's not drastically different than the inside. So like the buffers they come with, if you can't get KCl for some reason, that's approximately the concentration, those would be not horrible. Like the 4, pH 4 one, but not great either. If the electrode is to be used above pH 9, you should soak it in a high pH buffer. If it responds sluggishly, if it drifts or cannot be calibrated properly, the electrode needs to be cleaned. To be honest, for like academic labs, nobody bothers doing this. They just buy a new one because usually our pH probes are not more than like $200, and that's a really nice one for an academic lab. But some of these are made to be maintenance, and so you would get them out. For general cleaning, you would soak the electrode in 0.1 molar HCl or HNO3 for 30 minutes while stirring. If it's plastic, do not use HNO3, use HCl. To remove oil or grease, you would soak it for 15 minutes in a solution of 0.1 to 0.5% liquid detergent in hot water. And so that would actually remove the grease if you're using these for a lot of like organic solutions or things like that. We probably need to do that to our probes, to be fair. These are some of the causes of error in pH measurements. Wow, I am going super slow, aren't I? Okay, do you have any questions on any of this stuff? Yeah, so look through and let's more selectively take questions from you, okay? Tomorrow, I'll start off with that. I'll give it 15, 30 minutes. No, next time. The Monday. Not Monday. Wednesday. Because we have Martin Luther King. And let me know exactly what topic, if you have any topics that you're having any issues with. Make sure that you look at the questions here, the examples, so I can selectively like test yourself with the information. Okay. And I'll hit specific topics, but I just too much stuff in here. And some of this is not as important as others. And I just realized like I'm already at time, aren't I? I'll probably pick up here if you don't have any topics that you're specifically not understanding, because the other material is just the same stuff as I just talked about, and I don't think I can actually add anything of value to you talking about the how to maintain a pH probe. Okay. Did you try getting access to the homework yet?